All right, if we're going to find the exact area really between these two curves that are given, you've got a quadratic, you've got something linear, and then we got a couple of vertical lines thrown in there that could serve as interval values for how we're going to set up our definite integral here in a moment. But you can see I've already put the vertical lines in there. And if I think about how you would sketch out the two curves that are given, y equals x squared plus 3, going to be a parabola, right? Transformation would be it moves up 3 units. So if it's going to move up 3 units, now let's be consistent here with the color. We'll make this the blue guy. That would be a reasonably accurate sketch in the parabola, right? If you look at the linear part of it, the y equals x curve, using slope-intercept form, y-intercept would be 0. The slope is 1, so up 1 over 1. Draw our line. Trying to find the area between those curves, and also between our two vertical lines here of x equals -1 and x equals 1, we're talking about this little shaded region right here. So as I've been introducing this topic of the area between curves, I mentioned how sometimes there's a point of intersection that you're going to need to find. If you sketch this one out and just look at it, you know there's no points of intersection you really need to worry about, right? Your interval is set. If I want to find this area, for my definite integral, the interval I'm going to work with in terms of these x's is from -1 to 1, right? I just use those vertical lines as guidance. And then I'm going to take the difference between my two curves, being the quadratic and the linear one, and I'm basically going to go from top to bottom. So I'm going to take the x squared plus 3, that's the quadratic part. That's the top one. I'm going to subtract the x, because that's the linear part, in the bottom one. That's my setup to find the area. Doing so here with respect to x. Or now if I want to evaluate this, I'm going to take the antiderivative of the function I've set up. Not going to be too hard. In fact, the parentheses really aren't relevant at this point. You take the antiderivative of x squared, you get 1/3 x cubed. You got your constant there where you attach the x. And then we're subtracting x, so antiderivative of that would be 1/2 x squared. We slap our little bar on there to acknowledge the interval we still have to work with. And we get ready to apply the first fundamental theorem, right? And hopefully we've done enough of these problems at this point. We understand how we're plugging in. We're taking this one, we're plugging in for all the x's, right? We're getting that answer. Then we're taking this -1, we're plugging in for all the x's. We're getting that answer, and we're subtracting the two. Once you go through that process, do those calculations and subtract, let's see, our answer on this one comes out to be 20/3, assuming we're doing this all correctly. All right, so we got another one here, trying to find the area between two curves. We've got another quadratic. Got another linear function. And then we've got what appears to be an interval to work with, a couple of vertical lines we can draw in, x equals 0 and x equals 6, so I've already put those in. On the last one, as we sketch things out, we recognized that finding a point of intersection was not going to be necessary. But since we kind of glossed over that detail, let me take you through the process of finding a point of intersection if it applies. What you want to do is you want to take the two curves that you're comparing, you want to set those curves equal to each other. And now that you've set up an equation, you want to solve for x. So I've got a quadratic that's unfolding here. I'll move everything to one side. If I move everything to the left, subtract the 2x over, Subtract the 5 over, so that's going to be minus 3 now when I add on that 2. All that equals 0. Looks like we got something that's factorable. We factor this out, should be a minus 3 plus 1 combination, where if we solve for x, x would be 3 and x would be negative 1. Now we know ultimately when we set up these curves and kind of shade in the region that we need to analyze here to find the area, we're only going to be working between 0 and 6, right? So in terms of points of intersection, this negative 1 we don't have to worry about because that's not going to be between 0 and 6. But this 3 might be a big deal, right? Apparently these graphs are intersecting somewhere between 0 and 6, and where they intersect, x is going to be 3. So the point of intersection, if x is going to be 3, it'd be nice to figure out what y is and maybe plot that out. To figure out what y is, since they're intersecting at the same place, you could plug in either to this function or this function to figure out the corresponding y value. So say that I plug in to the first function. If I plug in 3 for x, 3 squared plus 2, that key point's going to be 11, right? So kind of going off my scale now, but here's where x is 3. We'll say, here's 11, right? We'll just make that up. That'll work. There's my point of intersection. So now, how is all this going to look? If I piece together this graph now of x squared plus 2, we know that's going to be a quadratic. We know that's going to cross the y-axis at 2. We're going to have a little parabola going through this point. Really going off my scale now to try to make this work. But you'll see why in a moment I'm doing this. Might be a good point in the program to remind you that graphing these out on your calculator too could be helpful. The 2x plus 5, the linear part, think about how you would graph that one. You'd start with the y-intercept at 5. Your slope would be 2, so you go up 2 over 1 from that point. But the thing is, the y-intercept's at 5. So as it relates to this first curve that we drew out, is it going to be above or below in terms of the y-intercept? Well, this y-intercept was at 2, right? I mean, come on, can't you tell, based on my graph, that this is at 2? You can't see that?
Oh, that's supposed to be the 2?
Yeah, that's supposed to be a 2. Like I said, I've kind of gone away from my scale that I originally set up to make this work. But if this is at 5, that's going to be higher. So obviously this is 5, right, as we squeeze that in. And we got our point of intersection right there, another point on this line. That line would have to be above the curve to at least get started on this interval from 0 to 6. But we know there's this point of intersection here, so it must drop below, past that point, the other curve. What we're trying to find the area of, if we're going from 0 to 6, we're finding the area here, and we're finding the area out here. So I tried to have everything set up for us in the first place, but well, that's the best we can do right there. So going down here, finding the area. You've got 2 shaded regions. So let's focus on the first one. If I focus on the first one, setting up a definite integral that would work for that one, the interval would have to be what? You're starting at 0, right? For the x's, you're going up to 3. Top function would be the linear one. Bottom, quadratic. So I'm going to take the linear function of 2x plus 5. I'm going to subtract the quadratic function, x squared plus 2. We're working in terms of x's, so we throw the dx on the end. That's the first one. Now, for the second one, we're going to have to add on another definite integral here that represents that area. So the interval on that integral would be what? 3 to 6. And now the curves have flipped, so the quadratic is on top, linear one's on the bottom. That's the general setup to find the area for each of these. Okay, so we've collected the like terms, you've transferred it over. We go through and evaluate these one at a time. Starting with this first one, got to take the antiderivative of the function. So going term by term with the negative x squared, that'd be negative 1/3 x cubed. With the 2x, that would just be x squared, right? Got your constant, attach the x. Throw the bar on there to acknowledge the interval. We're going to add to that, get this other one set up. Antiderivative term by term for x squared is 1/3 x cubed. 2x, got x squared. For minus 3, there's your minus 3x. Bar that goes on there, intervals 3 to 6. So like we discussed on the first one, assuming we know how the first fundamental theorem gets applied at this point, you're applying it for two separate problems here, really, and then adding those results together. I'm going to take 3 here. I'm going to plug in for all the x's, do that calculation. Take 0. Nice thing about plugging in 0 here is all that cancels out, right? You just get 0 back. When you plug in for that piece, let me see what we get here. I believe it was 9. Yeah. You plug in there, you get 9. We're adding on. Same idea for this next one. Take 6, plug in for the x's. Take 3, plug in for the x's, subtract 2. If you do that correctly, want to verify it, get 27 back, meaning your area between these two curves is going to be 36. Just that easy. All right, compare the first two that we did. 14's kind of unique. It's unique in the fact we don't have a couple of vertical lines to draw right away that could potentially give us an interval to work with, meaning this whole point of intersection idea that we need to find could be quite beneficial. We also have a situation where with these two curves, the way they're written, you may not be 100% sure of what you're dealing with. But for that first one, hopefully we could see how a line might be formed, right, if you solve for y. On the second one, you got the squared idea, so maybe a parabola is coming to mind. Now, sketching these out could be a little tricky, but everything is solved for x. And since everything is solved for x, it would be easiest when you're trying to find this point of intersection to actually take these two expressions that x equals, set those equal to each other. And then as you do the rest of this problem, work in terms of y instead. Right? The first two we've been working in terms of x. Normally we try to work in terms of x. It's quite honestly easier to see the whole top to bottom perspective. But on some of these, the way they're set up, if they're solved for x, let's go ahead and run with it. Let's work in terms of y. So solving for y here, I would probably clear the fraction first. If I clear that fraction, multiplying everything by 2, be y squared minus 6 equals 2y plus 2. I need some more room here, so take that out. Got a quadratic that's unfolding. Move everything over. Got y squared, subtract 2y over. Subtract 2 over to join that, negative 6, so minus 8. All that equals 0. Appears to be factorable. Since this one is factorable, goes to what? Minus 4 and plus 2. Looks like y is going to work out to be positive 4 and negative 2 from those factors, meaning we'll have 2 points of intersection here. Right? We're not going to exclude one of those values because we don't have any particular interval we're working on in the first place that would require us to do so. Finding the 2 points of intersection, we know for one point, y is going to be 4. For the other point, y is going to be -2, and since these curves are coming together at those same points, we can plug back into either of the original forms that we want to figure out x. So if I take 4 here and plug into this first one to figure out x, add on 1, obviously I'm going to get 5 back. And if I plug in -2, I'll just plug in the first one again, -2 plus 1, get -1 back. Let's go ahead and plot those points. If I plot those points, got -1, -2, got 5, 4. Actually stick with my scale here, that'll be nice. Got 2 points to work with, understanding that this first guy is linear. I know it's got to travel through these 2 points, so I could just draw the line through pretty conveniently. But this other guy, again, we might be a little rusty with this. That actually is a parabola, but the way it's set up, it's a parabola laying on its side. It's not actually a function. It's a parabola laying on its side where if you go through the transformations, at the very least, taking this -3 into account, that's going to move it over here. Move it over there as the vertex from where it originated as at the origin. Parabola is going to go through like this. Kind of just have to trust me on that one here as we get started, right? All right, so we're finding the area in here. And to find the area in there, now that everything is solved for x, I mentioned how it'd be nice to work exclusively in terms of y here because of the setup. Let's go over to this slide. Let's set up the area. We know, based on the points of intersection, if we're working in terms of y, these solutions we got here of 4 and -2 will set up the interval. So go from -2 to 4. And if we're working in terms of y, our top to bottom perspective has switched. Remember, use the positive side of the x-axis as guidance to give you the top part. Top part here is actually going to be this line if I'm using the x-axis and the positive side as perspective. It's going to be this line over this curve. So my linear part of y plus 1, that'll go first.
But that's because it's opposite, right?
That's because it's opposite, exactly. And we're going to subtract the curve, which is the 1/2 y squared minus 3.
Why does it start at -2?
All right, so we got the setup for the area. If we go through and clean this up just a little bit, and distribute the negative through. If I distribute the negative through, I'd have -1/2 y squared plus y. And distributing the negative to the -3, that's +3, so that's going to make this +4 when we add the 1 on, combine the like terms. Oh, what did I forget? I forgot to show my respect, didn't I? Need dy's on this one. Got the setup finally. Take your antiderivative on the -1/2 y squared. It's going to be a y cubed, so reciprocal of 1/3. I multiply the -1/2 in front, giving me -1/6. On the y, that's going to be 1/2 y squared. On the 4, since we're working in terms of y, attach a y. Interval still needs to be acknowledged. Now we plug in. We plug in 4 for all the y's. We plug in -2 for all the y's. Subtract those results. And in the end, we end up with a nice clean answer, 18.